Today we're going to talk about autonomous differential equations. Now, what are those? Well, they're a differential equation of the form y prime equals f of y. And if you think about the word autonomous, sort of the key word here is auto, self. So it's a differential equation where you have a differential equation for y prime. It's just in terms of its own variable, y. Now, can you solve these? Well, theoretically, yeah. It's a special case of a separable differential equation. However, in practice, it can get very dicey. And so the goal today is not to actually solve the differential equation, but rather to see, can we say something about solutions? In other words, maybe get some sort of qualitative understanding. So that's what we're after. Well, what can we do? Well, we'll look at what happens with our function. So f of y. So let's start with the first thing. Let's think about what does it mean when f of y is 0. So suppose I have a point where I have f of a equals 0. Now look at this function, y equals a. If you plug it in to the right hand side, you get 0. But the derivative of a constant is 0. 0 equals 0. So say, aha, it's a solution, right? Because it satisfies the differential equation. So you say, okay, so the zeros of our function tell us about constant solutions. Now, what about other solutions? What can we say? Well, what we can do is we can construct a phase diagram. Now, what does this look like? It basically is a line. So you say, all right, what we do is we draw our line, and we're going to have this be a line in terms of y. Now, we mark the zeros of the function. All right, so we can mark a couple places. Maybe we have some zeros here, here, and there. All right, so these are our zeros. Okay, so in particular, we've marked our constant solutions. And now we can say, well, what's happening in between? And if we think about what's happening, we say, well, our function, assuming we have a reasonable function, and of course, we'll only look at reasonable functions, the only way we can change sign is to go through 0, which means that for each interval, we can look at the sign of the function. Okay, so what's the sign of f? And really, when we ask about the sign of f, what are we really asking about? We're really asking about the sign of y prime. And so we say, okay, so that's really the sign of y prime. Great. So what do? Well, let's suppose we have our function, and we'll just assume some things are happening. Let's say y prime was positive below this point, y prime was negative, and then y prime goes back to positive, and y prime is positive again. All right, what does that tell us? Well, if we think about derivatives, it tells us how we're changing. So to say y prime is positive says that y is going up. Y prime negative, y is going down. All right, well, how does that translate into our diagram? Well, going up means moving to the right. So that says if I'm starting below this point, I'm going to drift towards that point. And if I start in between, where y prime is negative, I'm going to drift down. So my value for y is going to go down. So my curves are going to move towards that line. And so we can draw arrows. So the arrows match the signs. And we have some cases. So when we talk about phase diagram, we're really talking about this scenario. We have a number line, we mark the zeros, mark the signs of the derivative, add in the lines. Now, what do we have? Well, we have some behaviors. You'll notice at this point what's going on. Well, if we start a little bit below that point, we're going to move up. We're going into that point. If I start a little bit above, I'm going to go down. Again, moving in. So in other words, if we're near that value for y, we want to move towards that value of y. So we're moving in towards. And that is called stable. So this point here is a stable point, moving towards. All right, well, now let's go to the next point. What do we see? If I'm just a little bit below, I'm going to move away. I'm going to head down. Just a little above, I'm going to move away. I'm going to head up. So in other words, we have this solution, but if we're just off, we're going to start to veer away, move away from that solution. So you say, all right, well, what does that mean? Well, if we move away, we're called unstable, because, stable somehow says you should be coming in. Unstable, going out. So we say, all right, unstable. Now, there's another scenario which says, well, what if on one side you're looking like you're stable, and the other side you look like you're unstable? What do you do then? Well, you're half stable, or kind of stable, and we want to make it sound more fancy, semi-stable. So semi-stable is when we have different behaviors on the two sides. But you can think of it in terms of the arrows, right? Arrows pointing in, stable. Arrows pointing out, unstable. Arrows pointing in the same direction. So here they both point up, but you can also both point down. And that would be our semi-stable. And so now we have a pretty good idea of what happens to a solution. You give me an initial value for y, say my y is here, then I know what's going to happen is I'm going to move up. I'm going to head towards that value. Now, this is important. I'm never actually going to reach that value, but I'm going to get closer to it. So I move towards that value. And if I were to start here, what would happen? I'd keep going, and I'd just get arbitrarily large. So now we can understand roughly how it goes. And we'll see this a little bit more explicitly in an example in a few minutes. But before we leave, you might be feeling like deja vu. I've seen this before. What is it? Wait, where have I seen this? It feels kind of like first derivative test, because that's essentially what it is. It's basically a first derivative test, right? Because we're looking at the first derivative. And we say, well, let's look at the sign of the first derivative, positive or negative. Because first derivative positive means you're going up, first derivative negative means you're going down. So it's capturing the same behavior. And so if you say, oh yeah, it's first derivative test, and just treat it like that, you're good to go. All right, well, that's the basics. And with a few more examples, it'll become more clear about what to do and what's going on. So our first example. For the differential equation, y prime is y squared times y minus 3 times y plus 1. Find all of the critical points, classify each critical point as stable, unstable, or semi-stable, draw the phase diagram, and do a rough sketch of some typical curves. So this is a pretty packed problem. There's a lot going on. And there's some things that we didn't quite talk about, namely this last part, rough sketch. That's okay. We'll get to it. And we'll see that it's actually a little less intimidating than it might sound. All right, so let's begin. So when we're looking for critical points, what we're really saying is, when is the derivative 0? It's the same thing as the first derivative test. When we talk about the critical points of a function, so where is the derivative 0? So you say, okay, we want y prime to equal 0, or if you like, y squared times y minus 3 times y plus 1 equals 0. And it's our great aha. We already have it factored because they're nice. And we can say, oh, okay, so where are our critical points? Well, namely, they're going to be at 0. And 0 might be a repeated root, but we don't write it down twice because it's the same point. 3 and negative 1, right? That's the beautiful thing about multiplication. If you multiply and get 0, something had to be 0. So you set each part to be 0. Life is good. All right, so that's the first thing. We found them all. There aren't any others. Any other value for y that you plug in, you're not going to get y prime equals 0. So nice, cool. All right, the next thing is to classify each critical point as stable, unstable, or semi-stable. And then it says draw the phase diagram. But here's the thing. We can change the order. And oftentimes having the phase diagram makes the classification really quick. So let's do our phase diagram. So here we go. We draw a line. And we mark our points. So we have negative 1, 0, and 3. You don't actually have to worry about the spacing, but you do need to put them in the right order. All right, so what do? Well, you channel your inner Calc 1 student and say, oh, well, now I would test points in between. Now, does it matter which point? So, for example, between 0 and 3, should you pick 1 or 2 or half or 3 halves or square root of 2? Well, the answer is you can pick anything, because the beautiful thing is in between the critical points, it will always have the same sign. It's very consistent. And so it's just a matter of making sure you know what that sign is. Okay, so let's pick some nice numbers. Let's come here between 0 and 3. I see a number 1. And I say, okay, plug in 1. Well, 1 squared, positive. 1 minus 3, negative. 1 plus 1, positive. The value doesn't matter. It's all about the sign. We, as they say, we saw the sign, and it opened up our eyes. We saw the sign. So, remember, the product is negative. So y prime, negative. Good. How about something large? 4, a million, 5. 4 is pretty good. 4 squared, positive. 4 minus 3, positive. 4 plus 1, positive. Very optimistic here. Everything's positive. All right, how about between negative 1 and 0? Well, we'll have to do a fraction probably. How about negative a half? Negative half squared, positive. Negative a half minus 3 is negative, right? 2 negatives. Negative half plus 1 is positive half, positive. Okay, so here we go. Positive, negative, positive. Multiply, we're still negative. Okay, negative 2. Negative 2 squared, positive. Negative 2 minus 3, negative 5, negative. Negative 2 plus 1, negative 1, negative. Positive, negative, negative, put together, and we're positive. All right, so now we know the signs of y. And I like to translate that into directions. All right, so here, y prime positive means you're going up because you're increasing. So to the right, to the right. Y prime negative, going down. To the left, to the left. Of course, that's the danger with that song. You never know which one is it, right or left. Y prime negative, going to the left. Y prime positive, going to the right. All right, there we go. Now, if we pause here, this is our phase diagram. Okay, so this is good for reference. Now, before we go any further, there is one small thing I want to point out, which is you should keep track of something. We should be careful here and say, what is this axis here? And namely, these are y values here. So these are y values. This will become important as we go on in a few minutes. So just to keep that in mind. All right, so we've drawn the phase diagram. Good. And we need to, now we'll go back and do our classify. Well, we have 3 points, so we're going to classify 3 points. And what you do is you say, what happens to each side? So at -1, our arrows point in. All right, what does that tell us? Well, if the arrows point in, things go towards. Towards says I'm an attractor. Things are stable. So if I'm close, I'm going to come in towards that. All right, now for 0, what do we see? Well, the arrows are pointing in the same direction. They're pointing to the left. Now, it doesn't matter that they're both pointing left. They could both be pointing right. The key is they both point the same way. Since they're both pointing the same way, well, that means it's not stable or unstable. It's half, right? In between. And so that says 0 is semi-stable. All right, great. Well, how about 3? Well, again, we look at the arrows. They're pointing out. So if they point out, and it says even if you go a little bit off, you're going to move away. So you're very unstable. You're very sensitive. Sensitive to a small change. That's unstable. Whereas stable says you're not sensitive to a small change. And there you go. It's pretty quick. These problems are nice. Now, the last part. Do a rough sketch of some typical curves. Now, when it talks about typical curves here, we're saying draw solutions. Now, we don't have it explicitly solved. We could, if we were patient and we really wanted to, make progress into getting an implicit solution, and we could do partial fractions. But tonight, I'm not very partial to that. So we won't do that. So what are we going to do? Well, we're going to take advantage of the word rough that says it doesn't have to be exact. It just has to be kind of. All right, so here we go. We're going to draw our axis here. And so we've got our plane. All right, so here is our function. Now, it could be a function of t or x. Let's just follow convention. We'll put x. Here, we'll put y. Now, what I'm going to do, just to help me understand what's going on, is I'm going to take this phase diagram and put it back. Pick it up, put it down. Well, of course, I can't quite pick it up, put it down, so I'll just redraw it. And so we are going to mark the point. So we have 0, we have -1, we have +3, and we also had arrows, right? So we were going up towards -1, down towards -1, down from 3 to 0, and up from 3. So again, I've taken the phase diagram and put it right there. All right, good. So now we have this as a point of reference. And with this in mind, the rest is pretty quick. Where are the constant solutions? Flat lines. So constant solutions, flat lines, those are super easy to draw. And these are the critical points. So we say, okay, here's a curve, 0. Here's a curve, 3. And here's a curve, -1. All right, so those are 3 of our curves. Now, for any other curve, it's going to go in some way. So let's say I'm below -1. What should I be doing? I should be moving towards -1. So as I go from left to right, my curve should be moving up towards -1. So it should look something like that. All right, what about between 0 and -1? What happens there? Well, in that case, we're going down. So we should be coming from 0 down -1. Now, we can't be on 0, because if I'm on 0, I stay on 0. But I can be just below it, and then I can go down. So that we get something that looks something like that, right? Because we go from 0 down to -1. All right, well, what about between 0 and 3? Well, we should be going down. And so that's the key. We start near 3, head down towards 0. And there we go. And what if we're above 3? Well, if we're above 3, what are we going to do? We're going to go up. And so it says, look, if I start near 3, I'm moving up as I go from left to right. And there we go. So this is what the solutions generally, roughly, very roughly look like. But it gives a good idea what's going on. Now, one quick question for you to think about here for a second. What if I took this and I just moved it over a little bit? See, this is my advanced technology where I can slide back and forth. This is my budget for the year, so I hope you enjoyed that. Now, my question is, what's happening to the picture? Well, you might say, well, you're moving it back and forth. But in particular, are these still solutions if I shift everything left and right? And why? So they are solutions. Okay, so why are they still solutions? Well, here's where the notion that we have an autonomous differential equation comes into play. Because there's no x. So it doesn't depend where your x is. All I need to know is what your value for y is, and that determines your behavior. And so that's why shifting left to right, well, that changes your x value, but doesn't change what happens with your differential equation. So it is invariant under your horizontal shifts. So in this example, we have y prime is negative absolute value of y squared minus 1 arctangent of y. Now, maybe in a previous problem you were like, well, we had a chance, right? Partial fractions, maybe. Here, hopeless, hopeless. Forget about it. We're not going to make any progress. But that's okay. We can still answer these questions. All right, so we have 4 parts. So 4 times the amount of fun. So part A, find all the critical points. And it's acting as a reminder, these are constant solutions. So how do we do that? Well, of course, critical points, y prime equals 0. Well, that becomes the same as saying negative absolute value of y squared minus 1 times arctangent of y is equal to 0. And we take advantage of the fact that we have multiplication. So we say, all right, when does absolute value of y squared minus 1 equal 0? When does arctangent of y equal 0? Well, of course, the absolute value doesn't matter. When does y squared minus 1 equal 0? And the answer is y equals plus minus 1. When does arctangent of y equal 0? Well, we all know the arctangent function by heart, I'm sure, but it looks something like this. It's a part of the tangent turned on its side, and we see it crosses at one point, crosses at 0. So we have y equals 0. All right, great. So what's the answer for part A? Well, we basically have it written down. So for part A, we have y equals minus 1, 0, plus 1. Those are our critical points. They're also constant solutions. So y equals minus 1 is a solution. If we plug it into both sides, it's true. Similarly for 0, similarly for 1. All right, part B. Draw the phase diagram. All right, well, what do? For this, we draw a line. This is y on our axis here. We mark our 3 points and label them, but make sure they're in the right order. Negative 1, 0, 1. That's pretty easy to get that in the right order. We're fairly familiar with these numbers. And now the sign. Okay, well, some good news. Absolute value of y squared minus 1 is always positive because of the absolute value. Well, I guess we should technically say always non-negative. So it's never negative. So the only thing that can cause the negative is that negative in the arctangent of y. But see how the arctangent of y is positive for positive y values, negative for negative y values. So minus arctangent of y says that the derivative is going to be negative, right? Negative, positive, positive, and again negative, negative, positive, positive, and then we flip. So then it'll become positive and positive. So those are our signs. And now we draw our arrows to help us understand what's going on. So positive, we're going uphill to the right. Negative, downhill to the left. And there's our phase diagram. So there we go. Phase diagram. Great. Wonderful. Wonderful. Now, part C. Classify. Now, C is almost automatic. As soon as you have a phase diagram, you just read the arrows. And you say, okay, well, what's going on? Well, we see that for -1, our arrows point in the same direction. All right, so we can say that -1 is semi-stable. All right, good. Now, what about 0? Well, they're pointing in. Okay, so what is that? Stable. Great. And then +1. They're both pointing in the same direction, this time to the left. It doesn't matter left or right. If they're both pointing in the same direction, then that says it's semi-stable. So essentially what we're looking for is we're asking what's the behavior in terms of sign changes. And so what happens for semi-stable is that the sign doesn't change. Whereas if we go from a positive to a negative, that's stable. Similar, if you go from a negative to a positive, that's unstable. But there we go. All right, good. So we left ourselves plenty of space here to do part D because there's a lot of words here. So let's read what we have to do. For each critical point, we got 3 of them, all right. For each one, determine all y0 for which the solution to the ODE with initial conditions y of 0 equals y0 will have y approach the critical point as x goes to infinity. In particular, your answer should be an interval for each critical point. All right, so what happens? Well, think about the diagram. The phase diagram makes this problem actually not bad. Say, okay, let's start with -1. Now the good news is if you start at a critical point, you stay at a critical point. So the critical point is always going to be part of the answer for this interval. If I'm below the critical point, I'm going to move up. So any starting point below -1, I will move towards -1. So in the limit, as time goes to infinity, it will approach -1. So I'm going to get everything below -1 will go to -1. What about just above -1? You're moving away. So no matter how close I am, I'm still going to move away. So what moves towards -1? Anything up to and including -1. So the interval is -infinity to -1. All right. How about 0? Well, 0, that's going to be part of our interval. Say, all right, well, what happens below? Well, we're going to move up. So I say, okay, I'm going to be moving up to 0, as long as I'm just to the right of -1. So, okay, so it's everything a little bit above -1 and 0. And, well, okay, what about here? Well, again, I'm moving down, so I'm going to move towards 0. So I say, okay, in that case, what happens? Well, it's going to be everything but just before 1, right? Because if I'm 1, I'm not going to move to 0. I'm going to stay at 1. But even if I'm close, I follow the arrow, right? So if you have an interval, follow the arrow. If you know what your initial value for y is, follow the arrow. That will tell you what you approach. So our interval then is from -1 to +1. So if our initial value is anywhere from -1 to +1, in the long run, we head to 0. Finally, for 1, well, we know if we're below 1, we drift to 0. And then if we are 1, we stay at 1. Great. And if we're above 1, we drift down. So that tells us, oh, we're drifting down, and so we're going to move to 1. So our answer is everything starting at 1 and larger. 1 to infinity. All right, and that's the answer. That's it. Those are the intervals. Read your phase diagram. follow the arrows. So really the question is, pick your critical point and say, all right, where do the arrows point to me going into that critical point? And just say, okay, there's my interval. Life is good. Life is wonderful. For our final problem, we're going to do something a little bit different. And here we're going to have an extra parameter. So we say, all right, what's our differential equation? It's y prime equals hy minus y cubed. So h is something we can fine tune. So we're saying, okay, as you change the value for h, what happens? So in other words, what happens if h is 5 or 0 or -2 or something else, can we say? And so, all right, let's go through our process. So first off, we say, all right, we have an autonomous differential equation because right now, when we say h is a parameter, it's not a variable. It's a constant that we can pick. So we're going to treat it like a number. So we say, all right, what number is it? Well, it depends. So we're going to start by factoring. Well, we say hy minus y cubed. So this is the same as pull out a y, h minus y squared. Now, there are some cases. Well, certainly, if we want this to equal 0, because those are where critical points are, we see that y equals 0 is going to be a critical point. So 0 is always a critical point. On the other hand, here we have this h minus y squared. Now, for this to be 0, we would need to have that y squared equals h. All right. Well, here's where things get interesting. Because h could be negative, 0, or positive. Now, if it's 0, it's not very interesting because we always knew about 0. If it's negative, there's no more roots. Because for now, we're keeping it real. All right, so there's no solutions when h is negative. And then when h is positive, our last option, we can say, oh, well, then you can take a square root, and don't forget it's plus or minus. And this is here for h positive. All right, so we have our various things going on. All right, well, let's look at some cases. So let's look at 3 typical cases. So let's say h is negative, and we'll draw our phase diagram. So here I'm going to have y. And now, if h is negative, what are the critical points? There's just one. It's 0. All right, great. Now, what do you see happening? Well, if h is negative, h minus y squared is always negative. So when we plug in a negative value for y, we'll get a negative times a negative, which is positive. So y prime is positive. And on the other hand, if we plug in a positive value for y, we get a positive negative. So y prime is negative, which means that we have the following situation. We're going to be going up if we're below 0. We're going to be going down if we're above 0. All right, now that's h less than 0. H equals 0. Okay, well, this is actually really not hard at all. It says y prime is minus y cubed. And if you run it, well, minus a positive number cubed is negative, and then minus a negative number cubed is positive. And so what happens is we're going to be going up if we're below 0, going down if we're above 0. Great. All right. Kind of a deja vu type thing going on. But now we have the following. H greater than 0. And what can we do here? Well, we can mark, we'll have 0 positive square root of h and negative square root of h. Those are our 3 roots. All right, well, what can we say? We have to be a little bit more careful here. So we'll mark to the side. what we have. And if we factor carefully, we'll see that y prime is equal to y times h minus y squared, which we can write in the following way, namely square root of h minus y and square root of h plus y. All right, so now imagine you have a huge number, much bigger than square root of h. Well, we'll have a positive, a negative, and a positive. When we multiply all those together, we see, aha, it's a negative, right? Plus, minus, plus. So y prime is negative, which means that we're going to go down. Now, let's suppose we pick a number very close to 0. So in other words, much smaller than square root of h, but still positive. Well, we have a positive, and a positive. Because these are very close to square root of h. And so everything's positive. So we say, oh, okay, in that case, y prime is positive. And we're going up. Well, what if we're below 0? Say between 0 and minus square root of h, excuse me. Well, again, pick a number very close to 0, but negative. Well, we're negative, positive, negative, positive, positive. Yep, we were right. Got to be careful here. Square root of h is always positive. So y is a very small negative number. So that's negative, positive, positive, which means we're negative. We're going down. All right, and now a very large negative number. Very large negative number, negative, positive, negative. So minus plus minus all together makes positive. All right, y prime positive means we're going up. All right, now at this point you're probably like, okay, great. And is that it? Well, in some sense, yeah. Roughly speaking, we know what the behavior is. But here's the interesting thing. We can start to put all of these together. And so what we can do is we can draw a diagram. Now, be careful with your axes. And we want to label our axes carefully. So I'm going to have h be a parameter on the horizontal axis and y the parameter on the vertical axis. And now what we can do is we'll just think about what's happening. Well, our roots are as follows. We always have the root of 0. So that's y equals 0. And then we have the roots as y is plus or minus square root of h. And so that will look like this curve. So here are our roots. 0 plus square root of h minus square root of h. Now we can think about where does each of these fit in. In other words, each one of these phase diagrams we can incorporate into our picture. So here, this is an h less than 0. That fits in over here. And so what we see is that on this segment, if we are above 0, we move down. So it says, all right, we should be moving down. Now, if we do a similar thing with h equals 0, because that's sort of the threshold, so, all right, we mark that. That's going to be here. But again, what do we see? Well, we see that we're going to move down if we're above and up if we're below. And finally, we'll come to a typical one here. Here's a typical phase diagram, and that'll fit in over here. And what happens? Well, of course, now things get slightly more interesting. So we alternate. So we're going down, then up, then down, then up. So each one of these is a phase diagram. So essentially what this is going to be is it's the collection of all phase diagrams simultaneously. And what can we see? Well, we see some interesting things going on. we can start adding lots of arrows. And we say, all right, so initially below h is less than or equal to 0, then 0 is stable. Everything pulls in towards 0. After 0 then becomes unstable. And on the other hand, we have this plus square root of h. Well, that is now going to be stable. And this minus square root of h is going to become stable as well. So we can capture some really interesting behavior and some dynamics. So there's a whole branch of mathematics that tries to say, okay, what's going on? What's going on with this bifurcation? What's possible? What behaviors can emerge? And, well, it's an interesting subject in its own right. Not one we're going to go into, but one that at least we can wave to as we pass by. But for now, we're done, and that's the end for first order differential equations. But don't worry, there's always more. I'll see you again soon. Bye.